Hey folks, Kenny Johnson here, resident R&D nerd housed in marketing. I want to welcome you to today's webcast of the Keysight oscilloscope webcast series. This is a webcast that I did that's about probes. The webcast itself is entitled, What's That You Were Asking About Oscilloscope Probes? What it is it's a collection of tidbits of knowledge about probes. Here's the key takeaway, and I hope this sticks with you, is that if you're going to make a measurement that is something that's important to you, like you're going to write it down, you should probably be using an active probe. If it's just a relative measurement, is the 5 volts up, is the clock toggling, use a passive probe. And so the reason I kind of summarize that here is when you get into this, in this series, we'll cover things like, bandwidth, loading, response, connections, things like that in there. And what you'll see as we go through this is that active probes are worth the money you pay for them. If you don't feel like sitting through the whole thing, and one of those topics, you want to know about connection loading or connection bandwidth or offset range, there's time tags down the bottom. You can kind of fast forward to that. So good luck.
First, I'm going to try to give you some perspective as to why there are so many different types of probes out there. Then we'll spend a little time helping you understand some of the specifications. Not so much what the definition of that specification means, but how you can interpret that in specification in terms of how is this going to help, how can I decide if this probe is going to help me make a good measurement or not. I'm also going to share with you some rules of thumb to help you kind of, judge like good, better, best on some different probing solutions. We'll talk about some pitfalls that I've seen people stumble over so that hopefully you can avoid those. I'm also going to do my best to uncover some hidden gems. There's some things out there that products, bits and pieces that companies sell that can make your life a lot easier, and you might not know about those. So I'll try to uncover those, and then we'll spend some time at the end on general Q&A. So let me give you some background then around why so many probes. Myself, I'm a probe designer. And what happens is there's a lot of attributes in the probe that we're trying to balance. And some of these attributes increase proportional to the bandwidth of the probe. Consider that noise increases as the bandwidth of the probe goes up. So does its cost, its specialization. The development effort, of course, on an ultra-high bandwidth probe takes much, much longer than it does on a pedestrian bandwidth kind of probe. This list goes on almost ad infinitum. So there's features that increase proportional to bandwidth. There are also, on the flip side of this, there are attributes about probes that decrease proportional to the bandwidth. So for example, as you go up in bandwidth, probes tend to get smaller, the tip capacitance has to be smaller, the input impedance tends to be smaller, they're not as durable. Ultra high bandwidth probes, just by their nature of being smaller, aren't as durable as the general purpose passive probes. The number of choices that you have out there is more limited, there aren't as many accessories, and on and on. So what I end up with as a probe designer is something like this, where I've got this, as I'm trying to architect a probe, I'm trying to strike a balance of all these different attributes that I'm trading off. Some are getting better, some are getting worse as we go up in bandwidth. So given a measurement challenge that somebody has, and we're trying to design a probe that can meet that challenge, we're trying to do it at an affordable cost, make it usable, make it easily accessible, make it reliable. The end result of this then, of course, is that there is a plethora of probes. If I take an example like input range, so this would be the voltage that the probe can measure. We take something like the passive probe. We're all familiar with that. We got 4 of them for free with our scope. So the general purpose passive probe, they go up to about 500 megahertz of bandwidth, and you can usually measure the maximum input voltage on those is usually a couple hundred volts. Now if you want to go higher in bandwidth, you usually have to step up to an active probe. Active probes then go on out to ultra high bandwidth, and as they do that, they're more sensitive. They can't handle the high input voltages. If we consider the example of something like a high voltage probe, there's specialized high voltage probes. They can measure thousands of volts, but they tend to have much lower bandwidths. What happens then is you end up having to have different tools for different jobs. It's much like my workbench in my garage. You look at my workbench, I've got a lot of different wrenches, screwdrivers, pliers, various tools for getting different things done. The same is true when it comes to the oscilloscope probes. There's passive probes, there's active probes, there's single-ended probes, there's differential probes, there's passive high voltage, active high voltage, passive current, active current, specialized probes, on and on and on. Just like my workbench at home, where there's a variety of tools depending what I need. So the challenge then sometimes is picking out what probe you need for the right job. So in the context of what we're talking about, where we've got this wall of tools and we've got to choose the right tool for the job. Well, how do I choose the right tool for the job? Well, the way you start when you're talking about something like a scope probe is you go look at the data sheet, the specifications, the characteristics. If I take something like this passive probe here, we can see that the characteristics and specifications for that, it lists things like bandwidth and attenuation ratio, input capacitance, and so on. Now there's analogous list of specifications and characteristics for active probes. You see similar kind of things: attenuation ratio, bandwidth, input dynamic range. Farther down the list overlaps with things like the passive probe with input capacitance. So how do you determine then, how do you translate these specifications or characteristics into useful knowledge about, is this tool right for the job that I'm about to use it for? Well, that's what I hope to do next here, is we're going to talk about some of these considerations. The probe bandwidth, the probe loading, the connection to the target, attenuation ratio, dynamic range, offset, and ease of use, and how you can go through and look at the specifications and characteristics for these probes and translate this into useful knowledge about how to best use this probe. First thing we're going to talk about, probe bandwidth. So, when we talk about probe bandwidth, what we're talking about is the 3 dB point. Pretty universally accepted definition of the 3 dB point. In the context of probes, what we're saying is the 3 dB point, where we specify the bandwidth, is the frequency at which the output of the probe is diminished by 3 dB relative to its nominal response. Okay, kind of a windy answer. What does that really mean? Consider this: if I had a 1-to-1 passive probe or 1-to-1 active probe, the transfer function for the probe is 1 then. The output would equal the same as the input. So if I took something like a sine wave, and I took a low frequency sine wave that was 1 volt, and I measured it with my probe, the probe would output 1 volt. As I slowly dial up and increase the frequency of that sine wave, I will get to a point where I'll start to see the output of the probe be smaller than the input of the probe. And when I get to the frequency at which the output of the probe is 0.7 volts compared to that 1 volt input to the probe, I'm now at the point that I've found the 3 dB point for this probe. Now, keeping that idea in mind, we're going to build on that and kind of enrich this. There's a fairly universally accepted little formula or equation that you can use that says bandwidth times rise time equals 0.35 when we're evaluating a rising edge, and we're talking about the 1090 rise time. Or if we're talking about the 2080 rise time, bandwidth times rise time equals 0.45. Now what that's saying is that as the rise time becomes faster, the bandwidth or the high frequency content of that edge increases. So a faster rise time would be a smaller time number. That means the bandwidth has to get bigger. Let's look at an example then, what I can do with this little handy little formula. If I said I had a 5 nanosecond edge, well, if that's the rise time, I plug it into my little formula, solve for bandwidth, and that says the bandwidth of that signal is 70 megahertz. So the frequency content that goes into making that edge goes up to about 70 megahertz. Okay, so now I have a feel, if I know the rise time, I have a feel for what kind of bandwidth I need in my probe and my scope to be able to measure that rise time. Working the other way, let's say I've got something like a 500 megahertz passive probe. Well, knowing the bandwidth of the probe, I can work the other direction with the formula, and I can calculate that for that 500 megahertz probe, the fastest edge that that probe can measure will be 700 picoseconds. And I illustrate that with this screen capture on the right there, where I've got a system where I've got a 525 picosecond edge. I probe that with my probe, and the output from the probe shows me a 700 picosecond edge. Okay, so with this handy little formula, I can work it either way. I can calculate the bandwidth I need for that rise time, or given the bandwidth of my probe, I can calculate the fastest rise time that it can produce. Now, let's say you're saying to yourself, well, that's great, Kenny, but I don't know the rise time of my signal. What I know is something like clock frequency, right? I know the frequency of the clock that's running my digital system. Well, okay, I'll tell you how to answer that, but hold on. First things first. We have to go back a little bit and remember your Fourier series. Fourier series says I can build any waveform I want out of a series of sine waves. So in the example I've got here, I've got my original signal. And if I take and I look at the first harmonic of this, what I see is a signal that has about the same kind of period and duty cycle, but notice that the rising edges are much slower and the corners are rounded off. Now, if I add on top of this first harmonic, if I go out to the third harmonic, I can see now that I've got faster rising edges and my corners are getting crisper. If I go out even farther to the fifth harmonic, I can see that my edges are nice and fast, the corners are crisp, and I'm also seeing that detail on the top and the bottom of the waveforms. So with the Fourier series then, I build up a series of high-frequency sine waves, first, third, fifth harmonic in this case kind of thing for the square waves, and as I go higher in frequency, I get a more and more detailed square wave. Okay, so let's build on this a little bit. If we take an example then of I've got a system that's got a 100 megahertz clock. If you look at that screenshot on the upper left there, I'm measuring that 100 megahertz clock with a 100 megahertz bandwidth scope probe combination. What I'm seeing is a signal with a period appropriate for 100 megahertz, but it's just looking kind of like a sine wave. Now, if I have enough bandwidth, we move to that screenshot on the right where I'm using a probe and scope combo that has 500 megahertz of bandwidth. What I'm seeing is nice, crisp, square edges, faster rise times. So this is illustrating what we talked about there with that Fourier series. So what you can take away from this then is that the suggested bandwidth in analog applications is at least 3 times higher than the fastest sine wave frequency in your system. Or if you've got a digital system, what you do is you just say, I need bandwidth that's about 5 times my clock rate. So let's summarize this real quick, what we learned about bandwidth then. So if you're picking out a probe, you want to grab one that's got about 3 to 5 times the bandwidth in the system, the rep rate, the clock rate kind of thing. And also remember then that bandwidth times rise time equals 0.35. So you can either work your way over to figure out what kind of bandwidth you need if you know the rise time, or given the bandwidth that you got, you can figure out if it's up for the task for measuring a specific rise time. Now, the next one we're going to talk about was probe loading. This is one that a lot of users are aware of, but I think they often overlook a detail, and it kind of gets them into trouble. When I'm talking about probe loading, what I'm describing is the adverse effect on your signal, on your target, that occurs due to the presence of the probe. So I touch the probe to the target changes. With low loading, the change is imperceivable. With excessive loading, when I touch the probe to the target, I can change the behavior of the target in such a way that it might malfunction. If you take a look at what I present here on the screen, these are right out of a user's guide for our probe. We present a lot of this information for all of our probes. What you'll see is a simplified probe load model. It's a 3-element, just RL and C, and the model is shown down there in the lower right. If we start at the input of the probe and we move along, you'll see that the first thing we see is the inductance of the probe. Looking at that line drawing of the probe up above, that inductive element is representative of the inductance of the input pin and socket and connection trace at the front of the probe. The next thing we'll see is that there's a resistor and capacitor in parallel to ground. And the resistor for this particular probe is specified as 100 k ohms, and the capacitance is specified as 0.8 picofarads. Now that resistor is actually a discrete element that was designed into the tip of the probe to isolate the probe and circuit from each other to minimize the probe loading. The capacitance can be a combination of designed-in elements and parasitic effects of the probe. You know, there's some capacitance between the ground of the probe and the signal of the probe, just due to the presence of the metal next to each other. But here's the takeaway on this, is that if we look at this then, the impedance plot on the left there is impedance versus frequency. If we go over close to the left-hand side, where we're close to DC, the input impedance of that probe is 100 k ohms. What that means is when I touch that probe to your circuit, what DC is going to see is a 100 k ohm resistor to ground. Now as I start to go through and increase the frequency, let's say I'm just probing a sine wave. As I start to increase the frequency of that sine wave, when I start to get out to the megahertz kind of thing, what I see is that the impedance is starting to drop off. That's because, of course, the impedance of a capacitor is inversely proportional to the frequency. So as the frequency goes up, the impedance of that capacitor decreases. So at higher frequency, that capacitor starts to become an easier path to ground than that resistor. And we see that impedance start to drop. And you can see that all the way out then to the gigahertz, to where that bottoms out at about 165 ohms. Okay, so now you've got that data. What do you do with that? You can go look it up in a manual. Well, here we go through, and this is where people kind of get confused on this, and this is where I've seen it bite most people. Let's compare the passive probe and the active probe. Your typical 10-to-1 passive probe, 10 mega ohm input impedance, big fat resistor. People love that. Go look at that active probe there that I'm showing you. It's got 1 mega ohm. So at first blush, people would say the passive probe is going to have less loading. That's because of that 10 mega ohm resistor. But consider that capacitor. The capacitance of that passive probe is almost 10 times as big as the capacitance of the active probe. So again, considering that impedance changes with frequency, if we look at this chart, we can see that right there at about 10 kilohertz is where the impedance is the same for these probes. That's the crossover point. If we continued on out to where we're at 70 megahertz, a frequency that is well within the useful range of both probes, we can see that the impedance of the passive probe is 150 ohms, while the impedance of the active probe is 2.5 k ohms. So going back to just our example of a pure sine wave, if I had a 70 megahertz sine wave and I was going to go probe that with the passive probe is going to look like 150 ohms to ground for that sine wave. The active probe is going to look like 2.5 k ohms to ground. So even though the passive probe is a bigger resistor, that capacitance is overriding and contributing to the most of the loading. I'm going to illustrate this with a couple of screenshots. So, consider this green trace there. What I've got is I've got a special fixture where I'm able to run a signal straight into the scope. But that signal is also exposed so that I can touch it with my probe. So before I touch the signal with the probe, I can see that the signal has a 1.1 nanosecond edge. When I touch my active probe to that signal, that's the yellow trace, and you can barely see it because it hasn't changed much. So the yellow signal has a rising edge of 1.1 nanoseconds. So the passive probe has not disturbed the signal that I'm probing. Well, of course, that red trace then is what happens when I touch the signal with my passive probe. Now that trace is not what the passive probe is reporting, it is the actual signal. I'm observing the change to the signal when it is touched by the probe. And that signal slows down, it rolls over, and it is no longer 1.1 nanoseconds, it's now 1.5 nanoseconds. That's probe loading. In this case, the bandwidth, using our formula that we talked about previously, is 300 megahertz. If we look at this then, that passive probe looks like 50 ohms at 300 megahertz. The active probe looks like 600 ohms at 300 megahertz. So for probe loading, remember that impedance changes with frequency. So it isn't all just about a big R. You want to probe with a big R, but you also want to probe with a small c. That's going to improve your loading. Next thing we're going to talk about, connection bandwidth. Now, there's a concept here that I want to share, which is this idea of beware of the weakest link. I've seen people go through and spend good money on a really good scope. They've got a great scope on their bench. And they've spent good money and they've got a great probe attached to that great scope on their bench. And then they put some kind of flaky, just kind of not so good connection, accessory, or thing between their probe and their target. And what happens then is that becomes the weakest link. So the connection bandwidth is dominated by the weakest length. And most often, I see people make mistakes with how they make the connection to the target. I'm going to show you some actual examples here. This is based on data that comes right out of our user guides for our probes. We publish this kind of data so you can objectively make this kind of observation yourself. In the first shot there, I show the active probe that I was using in previous examples, our N2796A. And I've got it connected to a target using the twin lead adapter and some surface mount grabbers. The bandwidth out of that kind of configuration, 500 megahertz. That's pretty good bandwidth. Now if I make the connection shorter by removing those clips on the end, I can see that my bandwidth improves. It is now a gigahertz. Now if I go as short as possible for this particular probe, and I remove all those connection accessories and just replace them by the input pin and the ground pin for the probe, I now have 2 gigahertz of bandwidth. So obviously the takeaway from this, when it comes to the connection bandwidth, shorter is better. There's a lot of those those accessories out there. The shorter they are, the higher the bandwidth. Now, while we're talking about connections, let's also talk about connection loading. Those things you stick on the end of the probe, that's going to add to the probe loading. So, taking our exact same examples that we had before, the short connection, dual lead, and the grabbers, that's going to be a low loading kind of configuration. As we remove things, it's going to get progressively better. And of course, our shortest is going to be the lowest loading. Well, that's kind of qualitative there. Let's go through and actually show you some screenshots. So in the screenshots here, I've got my same fixture to where I'm able to run the signal straight into the scope, but that trace that the signal is on is also exposed so I can touch it with the probe and the connection accessories. So I look at the original signal, 1.1 nanosecond rise time. Okay, great. Now, the signal running into the scope, if I touch the trace with the dual lead adapter and those grabbers, so we've got long accessories in front, we can see that it changed the shape of that waveform and slowed it down, and that rise time is 1.7 nanoseconds. Again, these traces are the actual signal on the target. This isn't the signal that the probe is showing. This is the signal on the target. So it's changing the behavior of the target. Now if I shorten up the connection accessory, remove those clips, and just go with the dual lead, we can see that the rise time improves. It's 1.5 nanoseconds. When I go with the shortest connection accessory possible for that probe, we can see that I haven't changed the shape or the rise time of the waveform at all. The probe loading is minimized. The connection loading is minimized. Now, you're probably saying to yourself, well, that's great, Kenny, but I don't have a way to just run the signal straight into the scope and look at it. If I did, I wouldn't be using a probe. So how can I do what you did there and understand the loading of my connection accessories? Well, here's a simple experiment that you can conduct. What you do is take the probe that you want to use and the circuit that you're going to test. What you do is you go through and you measure the signal and save that trace to the scope. Then take a second of the exact same kind of probe. In this example, you can see where I've got 2 passive probes, and they've got that little grabber. So I hook up the first one with the grabber to that signal, and I save the signal to the scope. That's the yellow trace. Then I connect up the second probe, passive probe with grabber in the same place, and I observe the signal. And now I've changed the color so you can see it, but that's that red trace. Okay, that's with 2 probes attached. So the difference between 1 probe to 2 probes is approximately the same difference of 0 probes to 1 probe. So my original signal probably looks something like that white dashed line, and when I attached the first probe, it moved it down. When I attached the second probe, it moved down some more. So if you can kind of get just a basic feel for the magnitude of the loading if you've got the 2 probes. Put on one, put on the second, see the difference. The takeaway from this, though, of course, when it comes to connection loading, just like connection bandwidth, shorter is better. Now let's talk about attenuation ratio. Here's a sample of probes, various attenuation ratios, 10 to 1, 50 to 1, 500 to 1, 1,000 to 1. Why do we put different attenuation ratios on things? Well, the reason we do it is so that we can measure different voltages. You know, depending on what input you're using on the scope, you don't want to damage the scope. So you have to attenuate the signal or divide it down to the safe range for the scope. Now, the way we create the attenuation ratio, if I took something like a passive probe here, this is a 10 to 1 passive probe. And you can see out there at the tip, there's a 9 mega ohm resistor. And if you look over there towards the right where it says scope, you can see there's our scope of 1 mega ohm. Okay, so that's going to give us our 10 to 1 divider ratio. But it's a little more complex than that. What we need to do is create an impedance divider. So when we do that for like our passive probes, there's a ratio of 9 to 1 of the tip R for the probe to the scope input R. And then there's the inverse of that. The tip C is 1/9 the combined capacitance of the cable and the comp box and the scope itself. And so that's why you'll notice out there then that the C for that probe, that 9.5 picofarads, a lot of that is actually a discrete component that we have to put in there to create this impedance divider. And that's why the passive probe has so much higher capacitance than the active probe. In the active probe, we don't have to do it this way because we've got a probe amplifier in there that can act as the buffer for us. Now, if we look at these examples of 1 to 1, 10 to 1, and 100 to 1 kind of attenuation ratios, a 1 to 1 attenuation ratio is going to be very nice for measuring low voltage signals. Now, the problem with that, though, is it's also going to have low bandwidth, and that's because, like in a passive probe like that, that capacitance is going to be very, very large, and so it's going to have a much lower useful frequency. The sweet spot then is probably the 10 to 1. That's why most of the probes you come across are 10 to 1. It's a great general purpose probe and everything. And for something like a passive probe, you look at things up to 300 volts usually. Then when you go out to the higher attenuation ratios like 100 to 1 and on up, those are reserved exclusively for high voltage measurements. And the reason is because as we increase the attenuation, and this is kind of important, as we increase attenuation, so do we increase noise. Now you might say, but Kenny, a passive probe, how does that have noise? What happens is oscilloscope noise increases relative to the signal being measured by the attenuation ratio. Or stated another way, your signal gets divided down by that attenuation ratio, therefore scope noise is now that much bigger relative to your signal. To illustrate that point, here is a 50 millivolt peak-to-peak sine wave. I'm looking at it with my 1 to 1 passive probe, nice clean little sine wave. I measure that same signal with my 10 to 1 passive probe. It's all ratty and noisy and everything. And the answer that it measures for that peak-to-peak voltage is overstated by over 35%. And again, that's because the signal got divided down by 10 before it got to the scope. So the scope noise is now 10 times bigger with respect to the signal I'm measuring due to the attenuation ratio. So for attenuation ratios, use small ones for small signals, big ones for big signals. Next thing I'm going to touch on is dynamic range, and offset range. And these are in the context of active probes. And to understand this better, let's consider the characteristics and specifications that you'll typically see for an active voltage probe. First one I highlighted here is input dynamic range. For the probe I'm showing here are in 27, 95, and 96. That input dynamic range is plus or minus 8 volts. Now there's another thing on here that I've highlighted, which is the non-destruct maximum input voltage. That means I can go touch this probe to something as large as 20 volts without destroying it, but the useful input range is 8 volts. Okay, so I'm going to tie this together a little bit more here with one more specification, the offset range. So I can make use of that whole 20 volts by making use of probe offset. Allow me to illustrate. So just consider this scope screen here. If I take and I look at that specification that said input dynamic range, so plus minus 8 volts. Then we consider the part of the specification that said the non-destruct max input, plus or minus 20 volts. This range that is beyond the input range is the non-linear range for the probe. So the plus or minus 8 volts, that's where the response of the probe amplifier is linear. When you get outside of that, then you get non-linear response. Your measurements are going to be inaccurate. So what if we had a signal then that is swinging around back and forth up there in that nonlinear range? Well, I could make use of probe offset. What that does is that's going to remove the DC. And by removing the DC, it will pull the signal down back into the linear range of the probe so I can make accurate measurements. Consider this example here where I've got that signal, and you can see how it's clipped and distorted on the yellow tracer up on the top, where the part is up there in the nonlinear range of the probe. I take that same signal though, I dial in some probe offset, I move it into the linear range. Now it's my nice crisp sine wave shape that I was expecting to see. So input dynamic range and offset range then are considered together for the probe. And what it does then is it allows you to remove the DC content of signals that have a large DC offset so you can move it down into the linear range of the probe and also down into the center of the screen of the scope and zoom in on it to fill the screen with the signal for the maximum sensitivity. Final thing I'm going to touch on here when we're talking about this is ease of use. And I had an experience, probably a couple decades ago. We were working on some new scopes and some new probes, and went out to go talk to our users about these and share them with them. And the response was kind of interesting. They'd look at the scope and they'd say, yeah, I kind of expected to have more bandwidth, higher sample rate. I expect that. It's kind of like me when I look at cars. I expect them to have more horsepower and better gas mileage. And what people ask for is like, what did you do to make my life easier? And people quite often then get excited about some of the innovations that we've done in probing that make their life easier. And I'm going to touch on a few of those here real quick. The first one would be a category of probes that we've done for extreme probing conditions. Starting at the top there, just an example, is we've got our N5450B extension cables. What these are is a set of cables that you can connect to the end of our Infinimax differential probes, and you can go through and make measurements from DC to 13 gigahertz with your part in the chamber running from -50 to 150 C. And that's because what that cable does is it puts the active part of the probe outside the chamber so it's not affected by the high temperature. Another example of extreme probing comes about measuring super small currents. So we've got our N2820 and N2821 current probes. These are high sensitivity, high dynamic range current probes. They've got microamp sensitivity, and you can measure up to 100 amps with these current probes. And on top of that, you can make these current measurements on your target while your target is in the temperature chamber, running from -50 up to as high as 150. Now another probe that we've got like this for extreme probing, the N2796A, this is an active probe that can measure from DC to 1.5 gigahertz, and it can go from -40 to +85. And what's unique about this is the actual active circuitry on the end of the probe has been mechanically hardened so that it can withstand the temperatures in the chamber. The probe also has a cable that is about twice as long as the typical probe, so that you've got enough cable length to get from the chamber out to your scope. And then the final example of this extreme probing would be our N7007A passive probe. It's a passive probe with bandwidth of 400 megahertz, and you can use it in the chamber from temperatures from -40 to +85. And again, it has a longer cable too, so you can stretch out to the from the chamber to the scope. Some other examples of things to make life easier. These are ones that I appreciate them, but maybe this first one, I appreciate it just because I've got a few more candles on my birthday cake, and that's the fact that a lot of our active probes these days come with headlights. I can turn it on and off. There's a little switch or button just right there at the probe tip, and that allows me to illuminate the area that I'm probing and see it much better in these fine-pitch boards that I'm probing these days. The other thing, too, is that most of our probes come with pogo pins on the inputs and the grounds. That gives you kind of that independent suspension so that if your target is scooting around, your hand's a little shaky or something like that, you don't lose contact. You end up with a reliable probing connection. Another thing about making life easier is that we've got a line of passive probes now too that has a much smaller tip diameter. Your typical passive probe is about 5 millimeters in diameter down at the tip. There's passive probes that have 2.5 millimeter tips, so that it's not blocking your field of view. It's easier to see it, and you can also shove them into tighter spaces or get more of them closer together side by side. Then the other thing too about ease of use is that there's a lot of accessories out there that are made to go through and grab or clip or plug onto things. Some examples, this is just a few examples I show right there. My personal favorite, to be honest with you, is the one that is in the upper left there, that one that looks kind of like a gray clothespin. I really like that one. What it allows me to do, it's hard to get perspective for size in that picture, but that thing is, the tip on that is small enough that I can go through and grab onto 0402 parts on my board and probe them hands-free. So I can just clip it onto there, have my probe attached, and then I can go off and drive the scope. I don't actually have to hold the probe in place there. And in talking about that, not having to hold the probe in place, there's also some positioners out there. A lot of people don't know about these. They range from something very simple, like in that lower right-hand picture, where there's just a two-leg positioner that you can put around the probe that makes the probe act like the third leg of a tripod. We've also got some positioners, like in that picture in the upper right, where they act like phonograph arms. So you can put 1 or 2 probes in there, and so if your target moves around or shifts or whatever, the positioner will track with the target and you don't lose position. There's also a positioner, there's 2 pictures of it there on the left. That lower left picture, you can kind of get a feel for it. It's got a hand, a wrist, an elbow, and a shoulder. And that knob that's by the elbow, if I turn that and loosen that, all those joints go loose. So I can put my probe in the hand, and then I can go put the probe in any position I want. I turn that knob, it tightens all those joints, and it holds it in an infinite number of positions. The example in that upper picture is I'm probing a vertical board in a card cage situation. Myself, I actually use that positioner, by the way, for a lot of other things too, like holding my camera or holding things when I'm trying to solder. It's like a third hand. It's very helpful. So when it comes to these ease of use kind of things, look around, go check the probe case, the packaging that came with your probe, go search on the web, the manuals, the user guides, things like that. There's probably some accessories out there that were designed for that probe to allow it to do things that are kind of beyond what you normally imagine. In addition, there's also those extreme kind of probes out there that you might not be aware of, some specialty kind of probes that are designed to do a certain job and to do that job very well. So let's summarize some of these considerations real quick. So when it comes to bandwidth, remember the 3x to 5x rule for bandwidth, and that useful little formula of bandwidth times rise time equals 0.35. So you can, given one, you can calculate the other and figure out your need from there. When it comes to probe loading, a big R is your friend, but don't overlook the value of very small c. So you want to probe with big R and small c. Connection bandwidth and connection loading, those two go together. Shorter is better. Shorter is better. Attenuation ratio, remember that we use small attenuation ratio for small signals, big for big signals. You could use a big for a small signal, but your signal to noise ratio is going to be terrible because scope noise increases proportional to the attenuation ratio. Dynamic range and offset range. Remember that offset is very helpful for moving the DC content from the signal, so you can move it down into the into the linear range, and you can fill the screen with the signal. This is helpful for things that are like big signals, or if you've got small things like noise and ripple on a supply, and you want to move it down into the center of the screen so you can zoom in on it. And of course, like ease of use, look around, see what you got, but remember those loading and bandwidth trade-offs that we talked about. Now, all these things that I talked about, there's some resources out there to help you along with this. First one I want to point out is Keysight/find/scopes_probes. You do that, that'll take you straight to our oscilloscope probe page. It's got all the probes, all those accessories. It's got a lot of app notes, videos, things like that. So if you want to know some of those specifications or how to use it, go there. Another one that's a very, very useful link would be keysight.com/find/scopes-power. If you're making a power measurement using an oscilloscope, you need to use some specialized tools. Current probes, high voltage probes, power integrity probes, things like this. Go to this link. This has information about just those specialized tools with application notes and application videos about measuring power using an oscilloscope. So one other thing that I want to point out is that the screenshots you saw today, most of the screenshots were taken using our Infinivision series of affordable general purpose oscilloscopes. Our Infinivision scopes start with our 2000 series and move on up our 3000, 4000, and 6000. And as you go up in number or family, the bandwidth increase, and also does the richness of the feature set and the size of the screen and the versatility of the box. And so you can see a quick view of the family there. Also, though, in addition to the Infinivision family, we've also got our Infinium family of benchtop and laboratory oscilloscopes. And all these things I talked about probes, that applies to probes, whether you're going to put them to our general purpose instruments, our bench instruments, our laboratory instruments. These rules of thumb are all the same. And so at this point, I'm done with the prepared material, and we'll move into question and answer.
Thanks, Kenny. And for our first question, what is the highest frequency bandwidth of current Keysight differential probes? Is it 13 gigahertz?
Sorry about that. I had myself on mute for a second there because I didn't want to overwrite while you're doing the surveys. So the highest bandwidth for the differential probes, it's in our family of Infinimax probes. The ones that I referenced go to 13 gigahertz, or that I was showing today with that extreme temperature, but we've actually got a family that goes up beyond 30 gigahertz. So if you're actually out there at those ultra-high bandwidths, yep, we've got probes that go up in excess of 30 gigahertz of bandwidth. I didn't discuss them today because I was more in the context of the fundamentals, but everything that I shared about loading, connection, things like that, that applies whether it's 10 megahertz, 10 gigahertz, 20 gigahertz, 30 gigahertz. Rules are all the same. But if you're curious about the other probes and everything, go to that link that I was telling you about on Keysight there. Go check out the probes. You'll see all the ultra high bandwidth Infinimax family of probes.
All right. For the next one, what is the best way to detect a square wave outside of the dynamic range of an active probe? Clipping is not always easy to detect in this case.
So if I try to imagine this here, so the question is about detecting the square wave. How can I tell if it's clipping or not? So here's what I do. First of all, it's pretty straightforward if you go through and you're kind of just looking at the screen of your scope and you say, well, if going back to the specs that I talked about, I know what the input range for my scope is, like on that one, plus or minus 8 volts. Well, so is the top of that waveform, above 8 volts? Well, then it's probably clipping. I've also got the offset. So you can take that and literally just look at the screen and almost imagine some lines across there that are based on those specs. It's also usually pretty, in my experience, almost intuitively obvious when I look at it, just because it's the waveform doesn't look quite symmetrical, has been my experience. But I do know that some instruments are capable of showing you the range at which they'd clip. Some are not. That's why I kind of give you that. Probably the fallback would be to go to the idea of just looking at the spec and just realizing, if you're at a volt per division or 2 volts per division or whatever, how many divisions can I go up till I'm at the limit of the range for the scope? And if my waveform is at or above that, then yep, I'm clipping.
Okay. Can you touch on the bandwidth of the scope/probe combination? For example, using a 500 megahertz probe with a 500 megahertz scope versus a 500 megahertz probe and a 1 gigahertz scope.
Okay, yeah. So it can be kind of a rich discussion because it depends a little bit on the manufacturer's scope and probe, but again, it comes down to sort of that weakest link. Depending on what we'll call the roll-off of the probe, whether it's Gaussian or brick wall, it could be that you go through and you do the root mean sum of the squares, you RMS it, but we've tried to make it easy for you. What we do is that we put enough guard band on the bandwidth of our probes so that if you hook a 500 megahertz probe up to a 500 megahertz scope, the combination will be 500 megahertz. If you hook a 500 megahertz probe up to a gigahertz scope, it's 500 megahertz. So in that last example, the probe's the weak link, it's 500 megahertz. If you put a 500 megahertz and a 500 megahertz together, there's enough guard band there that it's 500 megahertz. So try to make it easy for you.
Okay. Question is, how do passive probes provide a 1 meg or 10 meg impedance without producing massive reflections?
Oh, yeah.
And have this characteristic impedance more than 100 ohms.
Yeah. So, that's actually pretty interesting. I remember the first probe that I designed when I started designing scope probes. I designed logic analyzer probes for many years before I designed scope probes. And first probe I designed was a passive probe. And I have to be honest with you, one of the things that taught me the most was I went back to an application note and patent application from Tektronix that went back to the 1960s. And he described it all for me. And I went, aha, it makes sense. And it's still done the same way today. And here's how this works, is that if you think about it, you're probing your signal. The signal is going to go up a cable. Okay, if it's a 50 ohm cable or some coax cable, it's going to go zipping down that cable, and then it's going to see that 1 mega ohm input impedance of the scope. That change in impedance is going to cause some reflections, and those reflections are going to go bouncing back down that cable, and then when they get to the end of the cable, there's going to be an impedance mismatch at your target, and they're going to go back and forth, and you get all sorts of ringing and ripple and stuff like that on your signal. It's going to look horrible. So what we do with the passive probes, first thing we do is we design the cable so that it's got as high an impedance as possible. There's a little bit of magic in that, but we do get impedances that are above the 100 ohms. And then the thing that we do is the center conductor is a lossy material. If you go take a passive probe, you cut it open, you look at it, that center conductor is going to be a very, very small wire, and it's not just your typical like copper wire. So the reason we do that lossy center conductor is so that when that signal goes up and it hits that impedance mismatch at the scope, it wants to go back down towards the target. Well, that little reflection then is going to get attenuated by that loss in that center conductor, and it's going to get smaller and smaller as it goes down towards the tip. And then when it hits the tip, it's going to try to go back up to the scope. And on that big round trip through the cable, basically that lossy center conductor and everything is going to kill that reflection. And so that's how it's done. That's how it's been done since the 60s. Still done that same way today.
All right, here's another one. Is there ever a time when you would want a larger capacitance on your probe?
Is there ever a time where I'd want a larger capacitance on my probe? I can't universally say that the answer would be no. Off the top of my head, it escapes me as to why I would want that. And I assume we're talking about that capacitance to ground that's in parallel with the resistor of the probe. I can't really think of a good reason. There's some weird corner cases where we'd use a capacitor in the signal path as a DC block kind of thing, or for DC reject. But as far as that overall capacitance, when we're designing probes, we work really hard to make that capacitance as low as possible, because that's parasitic and that's loading.
Here's one that I want to find out about. Is there a good way to check a probe to verify that its performance hasn't deteriorated other than to compare it with a known, undamaged, or a brand new probe?
Yeah, I know. Kind of like with my car, it's like, am I still getting the same gas mileage or horsepower out of this? I wish my car came with a what we call a PV procedure, and that's exactly what it is we've got performance verification procedures that we publish in the user's guide for our probes. And so what it does is it takes the key important characteristics or specifications in there and tells you how you can go verify those. In most cases, it's as simple as just performing what we call a user calibration. And that is that on the scope, there's a calibrator signal that comes out of the scope that has a fast enough edge on it and enough amplitude that we can do a lot of things with it to figure out if the response of the probe is correct or if it has changed or is incorrect. So not only do we use it to perform calibration on the instrument to where we'd store off in software some calibration factors about the probe, but you could also find out that if you can't get your probe to pass the user cal, then your probe is deteriorated. So you first pass, make use of the user cal. On our products then, what you do is you go through and you kind of poke the button associated with that channel, and then there'll be kind of a probe menu. You go poke that probe menu, and then there'll be like a calibration menu, and it'll walk you through. There's a little wizard there that'll walk you through the user calibrations. You can walk through those to make sure that the probe passes the user calibration. For some of our higher performance probes, there's a performance verification procedure that's necessary to have other equipment. So we're talking about the really, really high gigahertz probes, to where there's some other fixtures that you can buy that are necessary for these performance verification procedures. But that's the first thing I do, is I just do that, the user cal.
Okay. Here's another one. Do you ever use the 50 ohm port of the scope, and what sort of probe would you use?
Did you ever use the 50 ohm probe of the port, and what kind of probe would I use? Yes, so we use the 50 ohm port all the time. That's almost universally where the active probes connect. If you think about your oscilloscopes, most of them, the high impedance input, the mega ohm input, is the lower bandwidth input to the scope. So, for example, I've got a 6 gigahertz Infinivision scope sitting on my bench, and the 50 ohm path is the one that goes up to 6 gigahertz. So the 50 ohm path is where most of your active probes are going to go, so that you can get the bandwidth. The exception to that is some of the more specialized probes, like current probes or active high voltage probes. Those go to the, for example, like the high voltage probes, those go to the mega ohm path because it can handle a higher voltage input. So in general, active probes are what you can go stick on that 50 ohm path, especially because, too, you don't want to just hook a cable to that 50 ohm path and go hook that to your scope, because then that's like putting a 50 ohm resistor between your target and ground, and you're just going to load your signal way too much.
Okay. For switching power supply spur measurements, is it better to use a differential or a single-ended probe?
It's going to depend on the power supply, but in general, the majority of the times, the switching power supply is where you're going to go use a high voltage differential probe. Okay, and that's primarily for isolation reasons. You don't have a direct connection back to earth ground through that differential probe. So the majority of the things, like if you go to that that web link that I was pointing out, where it was like scopes-power, you'll see that our application notes we talk about, and there's a lot of them in there for looking at switch mode power supplies and everything. You're going to go through and use high voltage differential probes on that. Now, another thing with switching power supply, there's a kind of a subset of that, which might be, and I'll just touch this, is if you have a switcher. It's a DC to DC, but it's a little switcher. Now, in that case, there's actually a specialized probe out there that we make. It's our N7020A power rail probe that's used for looking at the at noise and ripple and spikes and transients that are on the supplies. So I don't know if they meant switching as in AC-DC or switcher as in DC-DC, so that's why I touched on both there.
Okay, great. Well, we have a whole bunch more questions on the list, but we're going to have to get back to them via email. We
Okay.
need to conclude this presentation.